In this video, we shall review basic control actions commonly used in industrial applications. Control action can be defined as the way an automatic controller generates the control signal. Remember a block diagram we have used in earlier lectures. A simple automatic controller can compute the error signal, that is the difference between the reference input and the actual output, and then amplify it to generate the control signal to be fed to the actuators. A component that prepares the error signal is indispensable in a feedback control loop. But the control signal can be obtained from this error signal not just by an amplification, but in many different ways. Among the most commonly used industrial control actions, one can mention on-off control, proportional control, integral control, or a combination of the last two, that is, proportional plus integral control. In some cases, proportional plus derivative control may be useful. You can also combine three actions together to obtain a proportional plus integral plus derivative control action. In this video, I will discuss and compare these control actions, their advantages and disadvantages. First, start with the on-off control action, which is also known as bang-bang control. Basically, it's a two-level control action depending on the sign of the error signal. If the error is positive, you apply the control as U1, and for negative errors, you apply the control as U2. This figure shows the switching of the control signal as a function of the error. In many applications, it is preferable to do this switching not at E equals 0. You can switch from U2 to U1 whenever the error becomes significantly positive, and the other way around, you can switch from U1 to U2 whenever the error drops down to a non-zero negative value. In other words, you introduce a differential gap to the switching of the control signal. Here is a typical waveform for the output you would get if you use an on-off controller. The thick blue line shows the reference value and the thin lines show the differential gap for switching. The sign of the error signal changes whenever the output passes the reference value up or down. Nevertheless, in switching the control action to derive the output towards the reference value, a small error around it is tolerated. Such an operation is reducing the switching frequency and is expected to increase the operational life of the relays and other switching components. One final note about the on-off control is that it is a nonlinear operation. Therefore, the techniques for linear systems which we have seen up to now may not be applicable to analyze a control system which uses an on-off controller. The simplest linear control action is proportional control, which generates the control signal as proportional to the error. The proportionality constant, K sub p, is known as the proportional gain. The transfer function of a proportional controller is also equal to K sub p. And as a block diagram, a proportional controller can be shown like in this figure. The control signal can also be made proportional to the integral of the error. This is known as integral control. Denoting the proportionality constant between the control signal and the integral of the error as K sub I, the transfer function of the controller will be K sub I divided by S. And this will be the block diagram of such a controller. You can combine the proportional and integral control actions to obtain proportional plus integral control. In standard notation, the proportionality constant of the integral part is written rather than k sub I as k sub p divided by t sub I. Therefore, the controller transfer function u of s divided by e of s can be written as k sub p multiplying 1 plus 1 over tis. And you can show the block diagram of a proportional plus integral controller as in this figure. An integral control action can be described as being more aggressive than the proportional control action. Let us consider a constant error signal which is equal to 1. In that case, if we use only proportional control, the control signal will also be constant. Now, if we also add integral control action, the control signal will be increasing with constant slope. In fact, the contribution of the integral control will be as much as that of the proportional control after ti seconds. That's why, besides calling Kp as the proportional gain, we call Ti as the integral time. You can also apply derivative action as combined with the proportional one. Again, the standard notation is such that the proportionality constant of the derivative action is written as Kp times Td. Therefore, the transfer function of the controller is Kp multiplying 1 plus Tds, which corresponds to a block diagram as here. Note that this transfer function is not proper, so the implementation of an ideal derivative action is not possible in practice. It can only be approximated. Assuming that the error signal is constantly increasing, for example, it is a unit ramp function, the proportional action used alone will also generate a ramp function. Since the derivative of the error signal is constant, we'll obtain the same waveform for the control signal if we add derivative action besides the proportional one. The offset of this signal to the control obtained under proportional control only will be Td, which is called the derivative time. And finally, you can combine these three linear actions to obtain a proportional plus integral plus derivative control. In other words, PID control. The transfer function of a PID controller can be written as Kp multiplying 1 plus 1 over Tis plus Tds. Note that this transfer function is not proper because of the derivative action, and it has a pole at the origin contributed by the integral action. If the error is persistently increasing, for example, if it is given as a unit ramp, then the proportional action will generate a ramp function. The proportional plus derivative action will also be a ramp of the same slope, but the proportional plus integral plus derivative action will be increasing in a parabolic way. We will now discuss the effects of these control actions, their advantages and their disadvantages in a bit more detail. Let us first start with a comparison of proportional and integral actions. For a system under proportional control, if the error signal would go to 0, the control signal would also converge to 0. But in a linear system, that would result in 0 output, which would lead to a contradiction for any non-zero reference input. Therefore, we conclude that proportional control must result in steady-state error in order to generate non-zero control action. On the other hand, for a system under integral control, even if the error converges to 0, a non-zero control signal can still be generated since the control signal depends on the integral of the error signal. Therefore, adding integral action to the controller eliminates the steady-state error. The price paid for this advantage is that the integral control may lead to oscillatory response, even to instability in some cases. To discuss these points further, let us consider a liquid level control system. This diagram shows a liquid tank with an inlet and an outlet valve. The input flow rate is Q bar plus Qi, and the output flow rate is Q bar plus Qo. In this notation, the operating conditions are shown by capital letters with a bar, and the perturbations around these operating values are shown by small case letters. So a steady in and out flow rate, capital Q bar, will correspond to a liquid level of capital H bar, and the difference between Qi and Qo will result in a change of the height as h. A controller is assumed to be measuring the height h and then commanding the input valve to adjust Qi. The liquid flow resistance of the output valve, shown as RL, can be defined as the ratio of the change in the pressure to the change in the flow rate through the valve, namely P over Qo. So RL times Qo will be the hydrostatic pressure of the liquid in the tank, that is given as rho gh, rho being the density of the liquid and g being the gravitational acceleration. Qo can be written as rho g over RL times h, and for notational simplicity we are going to denote rho g by RL as 1 over R. The change of the volume of the liquid in the tank can be expressed in two different ways. One of them can be the cross-section area C times dH, namely the instantaneous change in the height. The other one is the difference between the input and output flow rates times dt. We can equate these two expressions, divide both sides to dt, and replace Qo by h over R. Rearranging the terms, we can get a differential equation relating the change in the height of the liquid to the change in the input flow rate, namely Qi, as Cr dH by dt plus h is equal to R times Qi. Now we can take the Laplace transform of both sides under zero initial conditions to find the transfer function h of s divided by Qi of s as R divided by Crs plus 1. Now assume that the controller is tuned in such a way that the input flow rate is proportional to the error. That is, the system is under proportional control. This will correspond to such a block diagram where x of s is the desired value of the liquid level. The closed loop transfer function can be obtained as the feed-forward transfer function divided by 1 plus the open loop transfer function, which results in Kr divided by Crs plus Kr plus 1. Let us obtain the steady-state error to the unit step input for this system. The steady-state error E sub Ss is the limit of E of t as t goes to infinity. Therefore, it can be obtained by the final value theorem. To find the error signal, we can use the transfer function from the set point to the error, namely x of s minus h of s divided by x of s. In other words, 1 minus the closed loop transfer function, which results in Crs plus 1 divided by Crs plus Kr plus 1. For E of s, we can substitute this transfer function multiplied by the Laplace transform of the input, namely 1 over s. We can cancel the s terms in the numerator and the denominator to obtain the steady state error to the unit step input as 1 over 1 plus kr. So zero steady state error cannot be obtained under proportional control. Nevertheless, the error can be made as small as desired at the expense of increasing the proportional gain. Next, we analyze the system under integral control. That means the controller transfer function is now k over s. We proceed along the same lines. That is, first we obtain the closed loop transfer function as the feed-forward transfer function divided by 1 plus the open loop transfer function. And then the transfer function from the set point to the error signal as x of s minus h of s divided by x of s, that is 1 minus the closed loop transfer function. Note that both of these transfer functions are now of the second order, since the integral control brings extra dynamics to the closed loop. The steady state error to the unit step input can again be obtained by the final value theorem. Substituting e of s as the transfer function e of s by x of s multiplied by the unit step input, we will have a cancellation of s and 1 over s, but the limit this time will be equal to 0. In other words, the integral control action eliminates the steady state error to a step input completely. Next, we shall discuss the performances of proportional and integral controllers in case of disturbances. We will analyze these in an example of a DC motor control system and assuming torque disturbances. Again, first start with proportional control. Remember that in earlier lectures we have derived the transfer function of a DC motor as 1 over s times Js plus b, where J is the moment of inertia and b is the friction coefficient. We are interested on the transfer function from the torque disturbance to the output position, and we can write this transfer function as 1 over Js squared plus bs plus kp. Also, using the superposition principle and assuming r of s equals 0, we can write the transfer function e of s divided by d of s as the negative of the closed loop transfer function. Now let's assume we have a step disturbance of magnitude Td, that is d of s equals Td divided by s. We can use the final value theorem to obtain the steady state error in this case by substituting the transfer function from the disturbance to the error signal and the Laplace transform of the disturbance and cancelling an s in the numerator and the denominator. We get the steady state error as minus Td divided by Kp. So the proportional control cannot eliminate the effect of the disturbance at the output, and this effect is proportional to the magnitude of the disturbance. The error can be decreased, but at the expense of increasing the control effort. Let's see what happens under proportional plus integral control. So now the controller transfer function is Kp times 1 plus 1 over Tis. The transfer function from the disturbance to the output can be found again as the feed-forward transfer function from the disturbance to the output divided by 1 plus the open loop transfer function. The result is now a third-order transfer function since the integral part of the controller brings an additional dynamics. Again, E of s over D of s will be the negative of the closed-loop transfer function. Now, under a step disturbance, that is, if D of s is equal to Td over s, The steady-state error can be obtained by using the final value theorem, which after the substitution of E of s and the cancellations this time yields 0. In other words, by adding integral control action to the controller, the disturbance can be rejected at the output completely. But we should also note that adding integral control increases the order of the system. Therefore, complex conjugate poles may be introduced to the closed-loop dynamics, and oscillations may be caused at the output. We can even question the stability of the system. Therefore, let us now compare proportional and integral controllers from this point of view. At this table, we have a comparison of 3 cases where this controller is a proportional controller, proportional plus integral controller, or only integral controller. If G sub C is equal to Kp, that is, if we use proportional control only, the closed-loop transfer function will be of second order, and all coefficients of the denominator polynomial will be positive. That means the closed-loop system is stable regardless of the value of Kp. However, if we add integral control action besides the proportional control, the resulting transfer function will be of third order. That means the stability of the system will depend on the values of Kp and Ti, and the system may turn out to be unstable. And if we apply only integral control, we can show that the denominator of the closed-loop transfer function will have no S term, and by Raoult's stability test, that means the system is unstable for any value of Ki. In short, the tendency towards instability is increased as the integral action is emphasized in the controller. In other words, integral control causes oscillations in the response or make the system unstable. What about the derivative control action? Well, derivative action reacts to instantaneous changes in the error. By using it, it is possible to anticipate large overshoots ahead in time. Therefore, it can increase the control effort and can produce a counteraction before such overshoots occur. Nevertheless, also keep in mind that ideal implementation of derivative control action is not possible. By increasing the damping and preventing large overshoots, the derivative control action improves the stability of the closed-loop system. On the other hand, it is sensitive to ripples in the error signal or measurement noise, because such ripples, although they may be small in magnitude, will change quite rapidly and therefore have large derivatives. We have to also mention that in a steady state, one would expect flatline signals in the system, and therefore the derivative control action cannot affect the steady state error. To analyze such properties of derivative control action, let us consider an example where the planned transfer function is a double integrator. First, apply proportional control only. The feed-forward transfer function as well as the open-loop transfer function will be just Kp over Js square. So the closed-loop transfer function will be Kp over Js square plus Kp. Here we observe that the closed-loop transfer function has purely imaginary poles. That corresponds to a case where the damping ratio is 0. Therefore, the unit step response will result in sustained oscillations. Next, add derivative control action to the controller. The controller transfer function becomes Kp times 1 plus Tds. Obtaining the closed-loop transfer function, we observe that the denominator is still a second-order polynomial, but since the parameters j, kp, td are all positive, the closed-loop transfer function has complex poles with negative real parts. That is, The effect of derivative control is to increase the damping ratio. Now we revert to the example of DC motor control to evaluate the steady-state performance of derivative control action. This time we will express the controller transfer function in a non-standard form as Kp plus Kds. Again, let's write the closed-loop transfer function as the feed-forward transfer function divided by 1 plus the open-loop transfer function. And let us now find the steady-state error for a unit ramp input, that is, whenever R of s equals 1 over s square. We know that the steady-state error can be found by the final value theorem as limit as s goes to 0 of s times E of s. To find the error signal E of s, one can use the transfer function from the reference input to the error, which can be written as 1 minus the closed-loop transfer function. Substituting E of s and cancelling s terms in the numerator and the denominator and taking the limit as s goes to 0, we obtain as the steady-state error B over Kp. That means the larger the friction coefficient, the larger will be the error for a ramp input. And the error can be decreased by increasing the proportional gain. But more important than this, we note that the steady-state error is independent of Kd, the magnitude of the derivative action. So, as we said earlier, the derivative action cannot affect the steady-state error. On the other hand, by inspecting the denominator polynomial of the closed-loop transfer function, we can obtain the damping ratio zeta as B plus Kd divided by 2 times the square root of Kp times J. This, in turn, confirms once more that the effect of the derivative action is to increase the damping ratio. Let us continue with the same example to investigate the effect of zeros on the transient response. Here we write the closed-loop transfer function once more and arrange it in such a way that both the numerator and denominator polynomials are shown as monic. Noting that the square of the natural frequency of the system, that is omega n square equals Kp over J, we can write the denominator polynomial in a standard form. We can also call Kp over Kd as Z. Therefore, the multiplicative constant of the transfer function can be written as omega n square over Z. By substituting s equals 0, you can check that the DC gain of this system is unity. On the other hand, the zero of the transfer function is determined by the relative weights of the derivative and proportional control actions. In this figure, we see the unit step response of the system for different values of Z. In each case, the parameters are adjusted so as to give omega n equals 1 and zeta equals 0.5. The plots are shown for Z equals 1, 2, 4, and infinity. It is seen that although the natural frequency and the damping ratio is the same in all the plots, as the zero approaches the origin, it becomes more difficult to impose a steady-state value to the output. In other words, a zero closer to the origin tries to block smaller frequencies at the output. So this brings us to the end of this lecture. As you do after each one of these videos, review the exercises and examples in your textbook and check that you know what the basic control actions commonly used in industrial applications are, that you can plot the control action generated by proportional, integral, or derivative action for simple error signals, that you know what the effects of proportional, integral, and derivative actions on the transient and steady-state performance of the closed-loop systems are, and that you have an understanding of the effects of proportional, integral, and derivative actions on the stability of the closed-loop system.